In the last couple of videos we've been looking at some of what you might call the mathematics of quantum mechanics. We looked at the state that an electron can be in terms of its spin, and we considered the operators which, when acting on an appropriate state, can produce a value for the measurement of the spin component. We're assuming this eigenvector-eigenvalue type of equation, where the operator making the measurement acts on the state and produces the same state multiplied by a real number. That real number is then the measurement of the component of the spin, in our case +1 or -1, and that's all fine. However, with certain combinations of operators and states, you don't get a nice neat answer like this, where the right hand side is a constant real number times the original state. Instead, things can get messed up. It can even sometimes produce a new state vector as a result, possibly multiplied by some numbers as well. If this kind of thing happens, then the old state is not an eigenstate of the operator, and there is no eigenvalue, therefore no measurement. Up to now, when illustrating the operator measurement formula of the mathematics, we've deliberately chosen situations where the right-hand side replicated the original state in some way, and the real number multiplier was the measurement. However, it's not difficult to find situations where we don't get these nice, neat eigenvector-eigenvalue equations. Take, for example, the application of sigma x on the up or down states. The up and down states represent those situations where the spins are in the positive or negative z direction, and sigma x measures the x component of the spin. Such a question, such an attempt at calculation, may seem bizarre. Okay, in the last video we spent some time looking at finding the average or expectation value in such situations, but we probably know enough to realize that asking for an actual measurement like this, as opposed to an average, doesn't really make sense. What I mean is, it's logical to ask the question, what does sigma z do to the up and down states? Because they are up and down in the z direction, so sigma measures them. For example, sigma z on the up state gives +1 times the up state. It measures the spin as +1. But why would you want to ask the question, what does sigma x or sigma y do to the up and down state? Why would you ask what a particular sigma matrix does to a state that is known to be at right angles to what it's supposed to measure? Well, the only answer to that question is that we are going to need to know. It's going to be very helpful when we start to think about entanglement to know this. So let's work it out. Let's work through the basics of what happens when you try mathematically to measure the component of a spin at right angles to it. Before we do, you should note that this is the point where, more than ever, mathematical measurement, if I can call it that, departs from experimental measurement and will give us some strange answers. You can, experimentally, make a measurement of the component of the spin in, say, the x direction of an electron which is known to be in the up state, and you will have a 50-50 chance of getting the answer that the spin is to the right or to the left, +1 or -1 in the x direction. Similarly for an electron in the down state. But doing it within the mathematics does not match up with that result. It does something quite weird, so let's look at it. The first ones we'll look at are those very situations. Let's try and find out what sigma x would do to the up state or to the down state. We'll leave the question as to what sigma y would do for a little later. Here's sigma x acting on the up state and also on the down state. We want to know what would be the outcome of these operations of applying the x Pauli matrix to states that are essentially describing spins in the positive or negative z direction. Can't be difficult to find this out. We know the sigma matrices and we know the vectors that represent the states, so it should just be a case of doing the multiplication of the spin matrix times the state vector. Here's the mathematics for the first of these two, sigma x acting on the up state in terms of the matrix and vector multiplication. There's the Pauli matrix for the x direction, sigma x, the thing that measures the spin in the x direction, and there's the up state. It has complete upness and no downness in the z direction. So, using the rule for multiplying a vector by a matrix, we first multiply the top row of the Pauli matrix by the state vector piece by piece, which gives 0 times 1, which is 0, plus 1 times 0, which is also 0, so that gives us a total of 0 for the top entry of the result. For the bottom line, it's 1 times 1 plus 0 times 0, which gives us a total of 1, so 1 goes into the bottom entry of the result. And there's the result. It is the vector 0, 1. Now we should recognize this column vector, this final column vector. It's the state representing spin down. So we haven't actually measured anything, because in order for there to be a measurement, it would have to have given the same state afterwards, but multiplied by a real constant. This is definitely not the same state that we started with before the measurement was attempted. We started with the spin up in the z direction, tried to measure it in the x direction, and ended up with the spin down in the z direction. It's a new state. So we can say that if we try mathematically to measure the x component of the spin of an electron whose spin is pointing up in the z direction, it will flip it into a down state, at least mathematically speaking. Very strange. And now that we know this result, we could write it in a simpler way. Sigma x on the up state gives the down state. Look at this and try to get it into your head. Sigma x acting on the up state flips it to down. The same kind of thing happens when we start with the spin in the down state and we try again to measure the components of the spin in the x direction. There's the Pauli matrix again, for making a measurement of the x component of the spin, sigma x, and there's the down state in the z direction. It has complete downness and no upness in the z direction. Again, you can easily think through this matrix multiplication, and if you do, you'll find that the result is the vector 1, 0, which is the up state. Once again, there's no measurement. Starting with a down state, if you attempt this mathematical measurement of the spin in the x direction using sigma x, it changes the down state to an up state. It changes the spin from down to up. And again, we could write that more simply as sigma x acting on the down state gives the up state. So there's something really strange here that we need to be aware of and remember. Applying sigma x to either the up or down states flips them from one to the other. Let that sink in. Also, however, bearing in mind again that the states that we're really going to be interested in are the up and down states, the other half of our question is, what would happen if we tried to measure the spin component of those up and down states in the y direction? In other words, what would happen if we applied sigma y to the up and down states? Now, before we do the maths, just think about it. In some ways, there's not much difference between x and y, at least in their relationship to z. X and y are both at right angles to z, so you'd probably expect sigma y to do the same kind of thing as sigma x, which would be to flip the up to down and the down to up. Well, that's true. It does, but with a twist. Remember that when we were first looking at the various state vectors, up, down, right, left, in, out, there was something different about the y direction, about in and out. The state vectors for the spin in the y direction, the in and out vectors, were different from the state vectors in the x direction, right and left, in that they had a factor of I, the square root of -1, embedded in the state. Otherwise, they were very similar to them. For example, here is the state for the spin to the right in the x direction, compared with the spin inwards in the y direction. They're both a mixture of the up and down basis states, and they're very similar, except that the y direction one, the in state, has an I as the multiplier of the down component instead of a 1. You may remember that in a very simplistic way, we said that it's as though our two-dimensional Hilbert space has a third dimension. I shouldn't really say that, but it's as though it does, one in which we could imagine the I direction to be in, a bit like with complex numbers and the Argand diagram. It's certainly wrong to use that kind of language. We ought to say that our basis states exist in a two-dimensional complex vector space. Anyway, perhaps then it is not surprising that sigma y, the thing that would normally measure the spin component in the y direction and which itself has eyes in it, would, if you apply it to the up or down states, not only flip the spin from up to down or from down to up just like sigma x did, but would also throw in an I or an I squared as well. Remember, I squared is of course -1. Here are the equations which show the application of sigma y on the up and down spins of the z direction. Once again, the mathematics is easy enough to work through. There's sigma y acting on the up state, which, well, kind of gives the down state with an I instead of a 1. And we can write this, of course, as I times the down state. Similarly, there's sigma y acting on the down state, which, if you go through the matrix multiplication, gives something very like the up state, this time with a -I instead of a 1. This makes the whole thing -I times the up state. So, in a similar way to what sigma x did to the up and down states, you can see here that sigma y has indeed flipped up to down and down to up, but has also thrown in an I here and there. In fact, we can say that any mathematical measurement of the component of a spin which is at right angles to that spin will flip the spin in mathematical terms, and maybe throw in an I or two here and there. I don't mean real physical measurements with apparatus. I mean making a kind of mathematical measurement using the rules of quantum mechanics. Now we're not going to need the following, but as a final example of this, suppose we had a spin pointing in the positive x direction and we measured it in the y direction. We would be making a mathematical measurement of the component of a spin which is at right angles to that spin. Consequently, from what we've just done, you should expect that it will be flipped into a spin in the negative x direction and also multiplied by perhaps I or a couple of i's. Here's the proof. Sigma y acting on the right state of the x direction, when you go through the multiplication of the matrix and vector, gives this, which is really I times the left state vector. So it has indeed flipped the right state to the left state, and in this case multiplied it by I. As I said, that will not be needed later because we will tend only to need to consider up and down states when we consider entanglement, but you could check out the general rule that for any perpendicular measurement using the mathematics, it will always flip the spin and maybe throw in an I or two. And for comparison, you may want to remember that for any perpendicular experimental measurement using apparatus, there will always be a 50-50 chance of getting the answer +1 or -1. So the flipping of a spin mathematically in a perpendicular measurement, in a sense, compares with a 50-50 measurement of an answer one way or the other for a perpendicular measurement, if that makes sense to you. Anyway, pulling together all the mathematics that we will need, in other words, the mathematics that relates to how the three sigma matrices affect the up and down states, the basis states, we can write all 6 equations as shown in this table. Sigma x and sigma y, acting on the up and down states, do not give a measurement. They change the mathematical description of a state from up to down or from down to up, and sigma y throws in an I or two as well. On the other hand, sigma z on the up and down states does exactly what you'd expect it to do. It makes a measurement in both cases. It gives the same state afterwards but multiplied by a real constant, +1 or -1, the measurement. Anyway, these 6 equations are going to be very useful later when we start to think about entanglement. We'll have occasions when dealing with the mathematics of entanglement where we will need to operate with sigma x or sigma y on the basis states of up and down, the z direction states. We will need to know and use these 6 results, and we'll need to be convinced that they make sense mathematically. We should not need to refer back to the vector forms of these equations, such as this kind of thing, sigma x shown as a matrix acting on the column vector, the kind of things which prove the results to us. We should now simply be able to accept the basic results embodied in these 6 equations and realize that underpinning each of the 6 of them is a matrix multiplication which we now know to be true. This form of the 6 equations will be adequate. So accepting and having understanding of these will be part of how we will appreciate just a little bit of the mystery of quantum entanglement. So make sure you're happy with these equations in the mathematical sense. As we've said, however, don't expect the first 4 of them to make much sense when trying to match them to real-world experimental measurements. As was mentioned, we know from when we looked at the Stern-Gerlach experiment that a measurement of the component of the spin perpendicular to the spin direction would in practice always give a 50-50 chance of a positive or negative result. There's no hint of flipping the spin in practice. If you have a spin which is up in the positive z direction and you try to measure, say, the x component of that spin experimentally, then there will be a 50% chance of getting the result that the spin was in the left direction and a 50% chance of finding it was to the right. And that's what makes it difficult at times to get your head around all of this. Whilst we can probably accept the mathematics here, it's not easy to model what's going on. It's not easy to match it with reality. We can't really make sense of it when we try to relate it to practical measurements with apparatus, which themselves are confusing enough with 50-50 and all that. The last 2 equations, however, are not too bad in that respect. Measuring the spin in the z direction of something that is in the z direction, up or down, should logically give +1 or -1. Sigma z should indeed measure the z component of the spin, if that's what it's supposed to do anyway. If the spin is up, sigma z should measure it as being up and give +1. If it's down, it should measure it as being down and give -1. These 2 equations kind of match what we would expect experiment to do. However, the top 4 seem problematical, at least in trying to get your head around what might be going on. Even though these 4 equations here are sort of saying the same thing, that spin gets flipped, it's not so easy to rationalize what they stand for in reality. The 4 of them are saying that if you have spins that are up or down in the z direction and you try using the mathematics to measure the spin component in a direction perpendicular to the z direction, x or y, then that mathematical measurement will flip the spin from down to up or from up to down and will multiply it by +1 or by I or by -I or whatever. That's weird, and it doesn't seem to match reality. This all means, I suppose, that we shouldn't really try to match up what I'm calling mathematical measurement with experimental measurement. Believe both, but keep the 2 separate in your mind. Perhaps it's worth contrasting these 6 equations with another 6 that we had early on, just in case you start to mix up the 2. I'll put a box around these with a heading about flipping, the word that applies at least to the top 4 equations. That heading, however, does not apply to these equations, which relate to a particular sigma matrix being applied to a state in that direction, so that each of these 6 equations correspond to a measurement. I'll also put these in a box, but with a heading about measurement. You can see in this list each sigma is acting on an eigenstate of the sigma, so that each gives a measurement of either +1 or -1. This list, however, is different. It shows each of the sigmas acting on the basis states, the states in the z direction. The bottom 2 do constitute a measurement, but the top 4, sigma x and sigma y on the basis states, do the flipping. It's this list, especially the top 4, that are going to be very important, and we're going to be looking at them quite a lot when we eventually get to entanglement. We may always wonder why, mathematically, a spin gets flipped when we attempt to measure it in the direction perpendicular to it, but it's something that we need to get embedded in our minds. Right, this next short section will be yet another very important idea in relation to thinking about 2 entangled electrons later on. when we eventually get to entanglement. It relates to an important idea about a single electron that you must be confident about before moving on to thinking about the state of two entangled electrons. We've said again and again that if you have a single unentangled electron, then it will have a definite spin direction in space, in real space. You may not know what that direction is, because you may have no knowledge of the history of the electron, but it will have a definite direction, at least in the sense that there will be some direction in space where, if you measure the component of the spin in that direction, you will definitely get the answer +1 with 100% probability. We've discussed a lot about the fact that you cannot confidently find that direction experimentally unless you have lots of electrons, which were all guaranteed to be pointing in the same direction. In other words, electrons which have been prepared in the same state. With just one electron, you will always get the answer +1 or -1 in whatever direction you choose to measure the component of the spin. You won't know what direction it was in before you measured it. However, we said that if you had lots of identical electrons, you could take a group of them, measure each one in a particular direction, some would be plus, some would be -1, and you could work out the probabilities for +1 and -1. If you then did the same for another group of electrons, but this time measure a different direction in space, you would then get different probabilities for plus and minus in that direction. Doing this again and again for different groups of similarly prepared electrons, each time choosing a different direction, would allow you to home in on the direction in which all of these electron spins had been pointing before you measured them. Once you found that direction, if you then took another group of the prepared electrons and measured the component of the spin of any one of them in that direction, you would always get +1. You would know, within statistical error, what the direction of the spins had been before you measured them. The point is, and the language I shall use is, that a single unentangled electron always has a definite spin direction, even if you don't know what it is. Yes, probability comes into quantum mechanics a lot, but not as regards the question as to whether a single electron has a definite spin direction in that sense. That's experimentally a fact. But what about in the mathematics of quantum mechanics? Is it possible to show from the mathematics that any single electron must have a definite spin direction? Well, the answer is yes. And let me illustrate. Here is perhaps the most general state we can write down for an electron in terms of its spin and using our Z basis of states. The general state is some constant A times the up state plus some constant B times the down state. A and B can be complex numbers, and they must satisfy the normalization condition A star A plus B star B is equal to 1. Now my question here is this. Given this general state, can we show from the mathematics that there must exist a direction in space where a measurement of the spin would definitely give the answer +1, 100% of the time? In other words, can we prove that there must be a direction in which the spin definitely points? Well, the sigmas are not going to help us to show that on their own. Sometimes we don't get a measurement at all when we use them on the state. Sometimes the state changes. What will show it, however, is the expectation value, sometimes called the average value. Let me remind you of what that is. You will recall that if the spin is pointing, say, in the positive x direction, and we measure the component of it in the z direction, there will be a 50% chance that the spin was up and a 50% chance that it was down. We've emphasized the fact that these two 50-50 answers don't show up in the mathematical measurement using the Sigma Matrices. However, for this electron with the spin in the positive x direction, we can say that the mathematics does show the 50-50 split in the coefficients of the up and down parts which make up the x direction state. You may recall that this is the state vector for an electron spin definitely pointing in the positive x direction. This 1 over root 2 squared gives the probability of getting an up measurement of the z component of this right pointing electron. It's a half. And this 1 over root 2 squared gives the probability of getting a down measurement, also 1/2. We also said that if, as this expression for the right state implies, the electron appears to spend half its time up and half its time down, then on average the component of the spin in the z direction must be 0. It must have an average value of 0. We demonstrated this early on when we went through some rather repetitious exercises on calculating expectation values. For example, we showed that for a spin in the positive x direction, the expectation value of sigma z was 0. That seemed fair enough. Now contrast this with the situation where the electron is, say, completely in the down state. In that case, the state vector is simply given by the down state. For this, the electron is definitely pointing downwards all the time, so that on average the component of the spin in the z direction must be -1. Again, we showed this by simple calculation earlier, that the expectation value of sigma z for this down state is -1. If we had done it with the up state, then the average would have been +1. So accepting all of that, I want to pose the question, could we possibly have an electron in some state or other, some particular state, where the spin was such that the expectation values of all three components of it were 0? Could we have the expectation of sigma x 0, the expectation of sigma y 0, and the expectation of sigma z 0 at the same time? Think about that. If this were the case, and I'll say right now that it can't be for a single unentangled electron, if this were the case, there would be no direction in space where the average value of the spin was 1. Every direction in space, not just x, y and z, but all others which would be made up of components in the intermediate directions, all other directions would have an average value of 0. In that case, if it were possible to have all of these three things equal to 0 at the same time, then such an electron would not have a definite spin direction in real space. It would mean that if we measured the component of the spin in any direction at all, we would always have a 50-50 chance of finding the spin pointing in that direction. This means that when I ask the question, is it possible to show from the mathematics that any electron must have a definite spin direction, then the answer is yes. If we can show that it is impossible for the expectation values or average values of all three sigmas to be 0 at the same time, in other words for the same electron, then we will have shown that a single electron must always have a definite spin direction. Now make sure you're happy with that argument. If we can prove that the three can't all be 0, then we will have shown that the spin must have a definite direction in space. So let's try it. Let me try and prove that all three of the expectation values can be 0 at the same time. I'll fail because they can't be, and it will show that the single electron must have some definite spin direction in space. We'll start with a general state of an electron, A times the up state plus B times the down basis state, where A and B can be any complex numbers, and if we want the state to be normalized, we would require that A star A plus B star B is equal to 1. However, we can relax this condition of normality and work with the unnormalized state. It will make the mathematics easier, and we're allowed to do this because we will be setting any results to 0. We're trying to prove they're all 0 so that any multiplying factors are not really relevant. To put it in crude terms, it doesn't matter for this exercise if this general state does not have a size of 1 in Hilbert space. For further simplification, we can factor out the A coefficient, and then this general state could be written as A into the up state plus B over A times the down state. We can then define the ratio of beta A to be the complex number C, making the general unnormalized state equal to the up state plus C times the down state. You'll notice that I've dispensed with the outside multiplier A, for the same reason that normalization is not important for this exercise, because we'll be setting things to 0 to try and prove that all three expectation values are 0. We'll now ask the question, is it possible to show that we cannot have all three expectation values of the spin components of this state equal to 0, or can we find a value of this complex number C that will allow all three expectation values to be 0? Let's see how it might be done. You should recall that the way to find the expectation value of an operator for a particular state vector is to sandwich the operator between the state written in two ways, the bra vector of it to the left and the ket vector of the same state to the right. Here it is working out the expectation value of the x component of the spin for the general state, the average of sigma x. Sigma x is between the general state written in the two ways. If we put into this our expression for the general state and use some different brackets to help the layout, we get this. The Pauli matrix that measures the x component of the spin is sandwiched between the bra form and the ket form of this general state. And you'll notice that the bra form has had to have the coefficient C complex conjugated. We evaluate this first by applying sigma x to the general state. This is easy because we know what sigma x does to the up and down basis states. It changes up to down and down to up, a straightforward flip. So after sigma x is applied to the whole ket on the right, we're left with this. Now, having applied the sigma x, it of course disappears, and you can see that the up has gone to down and the down has gone to up. All we have to do now is to evaluate this inner product of the bra with the new ket. You should recall that the inner product is a bit like the scalar product in ordinary vector multiplication, and in doing this we're going to get ups and downs multiplying one another together, and our rules for that kind of thing are these. Up with up gives 1, down with down gives 1. The same two states in Hilbert space are a bit like two ordinary vectors in real space. They're in the same direction. The dot product of such ordinary vectors would give a number as the answer, and in the same way this inner product, because these states are normalized, gives the number 1. On the other hand, up with down gives 0 and down with up gives 0 because these states are orthogonal. These are a bit like two ordinary vectors in real space which are at right angles to each other, and the dot product of them would give 0. So in our calculation, the only contributions from this inner product will come from up multiplications and down multiplication. And the final answer for the expectation value or the average value of the components of the spin in the x direction comes out to be C plus C star. You can check that for yourself by looking at the four terms that would come out of the bra-ket multiplication, or inner product as it's called. Now if you go through the same exercise for the expectation values in the y and z directions, you get that the expectation value of sigma y is I times C star minus C, and the expectation of sigma z is 1 plus C star C. So these three expressions give the expectation values of the three sigma matrices for this unnormalized general state. Now what we've been saying is that for the electron to have a definite spin direction in real space, all three of these equations cannot be 0 at the same time, whether they're normalized or not. If that is true, it means that if we try to force these three things to be equal to 0, then the three equations must be impossible to solve for the complex number C. Let me set them equal to 0. Only if all three of these expectation values are 0 would we be able to say that there is no direction in space where the spin of the electron is definitely in that direction, no direction where we would get the answer +1 every time we measured it. If these equations cannot be satisfied, then there must be a direction in space where if we measure the component of the electron's spin in that direction, we would always get +1. The electron would definitely have a spin direction. So can these three equations be satisfied? Well, we know that C could be a complex number, so that C and C star can be written in terms of their real and imaginary parts, which we'll call C1 and C2. If we then substitute these into the three conditions, they then become this expression, which after evaluation requires that 2C1 is 0, 2C2 is 0, and 1 minus C1 squared minus C2 squared is also 0. So the question is, can we find values for C1 and C2 such that these three equations can each be 0 for this general state? Well, you can see that C1 and C2 would both have to be 0, which essentially means no C coefficient at all, and that alone is problematical. But that, of course, is not all. The third condition would then say that 1 minus 0 is 0, which makes the whole thing nonsense. The conditions cannot be satisfied for any values of C1 and C2, and that means for whatever the values of A and B are which make up the complex number C. The three expectations or average values of the spin in the direction x, y and z cannot all be 0 at the same time. And this means that there must be some direction in space, it might be x or y or z or some mixture of them, some direction where if you measure the component of the spin in that direction, you will always get the answer +1. This demonstrates mathematically that a single electron always has a definite spin direction in real space, even if you don't know it. As we've said before, of course, it may take you a while to find out the direction experimentally. Because any individual measurement involves probability, and because you'll always get a +1 or a -1 answer anyway, you'll need a large number of identically prepared electrons, and you need to work your way through groups of them in order to home in on the actual direction that the spins were pointing in before measurement. Now I realize that this result, that electrons have a definite direction in space for their spin, may seem quite trivial. You had probably already believed it anyway. However, it is extremely important that you are convinced of it, both in experimental terms and in quantum mathematical terms. Because when we come later to think about the entanglement of two electrons, something very strange happens. The results from the mathematics of an entangled electron will be entirely different. And this will also be the case for any experimental measurement. In other words, for an electron in an entangled state, we will find later that all three of the average values of the three sigmas for each of the entangled electrons are equal to 0, implying that there is no direction in space for the entangled electron where if you measure the component of the spin of it, it would definitely give +1. You will always have a 50-50 chance of +1 or -1, but that is for later. This result here of finding that you can't have all three sigmas equal to 0 for a single unentangled electron is important, and you need to feel reasonably confident about it so that you will appreciate the big distinction between this and an entangled electron when we get to that later. Before we do, however, I'd like to try and consolidate even further this idea of finding the average value, or the expectation value as it's often called. To do this, it might be good to look again the Larmor precession of an electron in a magnetic field and deal with it not classically as we did before, but quantum mechanically, by seeing how the mathematics of quantum mechanics explains it. Now, if you don't feel you want to go through this, especially as it brings in one or two other ideas from Schrodinger's equation which aren't strictly needed for the way I'm going to tackle entanglement, then feel free to go to the end of this video and move on to the next one. But if you don't stick with it, however, you'll be left with an entirely classical view of precession, and you'll miss out on some discussion which re-emphasizes the concept of the expectation value, which might be useful once we get on to entanglement of two electrons. So first, a reminder of the classical side of things which we covered much earlier on. In an earlier video, we did a classical analysis of precession to try to understand what was going on. We envisaged the electron as a spinning charged mass with an associated magnetic moment and angular momentum. The calculation, although based on this flawed classical assumption, worked out fine and actually gave the correct answer for the Larmor frequency omega, providing we included the g factor from quantum mechanics, which has a value of almost exactly 2. If you remember, this omega is the angular frequency of the precession of an electron of charge E and mass me when placed in a magnetic field B, with its spin at some angle to that field. Note that the angle is not contained in the formula. The frequency of precession is the same for any angle to the field. We calculated that for a magnetic field of 0.1 Tesla, the frequency of precession, omega over 2 pi, is about 3 gigahertz. It is precessing roughly 3 billion times per second. We said at the time, even though our calculation gave the right answer, the classical assumptions within it couldn't really be said to be what was going on with the electron. It should not really be thought of as a spinning charged mass. As far as quantum mechanics is concerned, the whole system of electron spin should be treated differently. And we've said we'd return to this idea of Larmor precession once some quantum mechanics had been introduced. Before I do that, however, let me remind you a little bit of what we did to get the Larmor frequency from that classical consideration. It's probably worth saying that to illustrate this, I use blue arrows for the spin direction because I'm considering angular momentum to stand for spin rather than magnetic moment. I have tended to try and consistently use red arrows for spin magnetic moment mu and blue arrows for spin angular momentum s, which is 8 bar over 2 for the electron. In our classical discussion, we considered an electron situated in a magnetic field B, which was pointing in the z direction, and the electron spin was at an angle theta to the z direction. The analysis involved the classical forces due to the electron's magnetic moment mu in the magnetic field, as well as its spin angular momentum s. The spin angular momentum s is in the direction shown by the blue arrow, and you should remember, of course, that the magnetic moment mu of an electron would have to be pointing this way. This means that the torque on the electron is clockwise as we look at it, and is therefore a vector into the screen. In the diagram for the analysis, the positive z direction is upwards, the positive x direction is to the right, and the positive y direction is once again into the screen. Theta is the angle of the spin s to the z-axis. It's shown here with the spin angular momentum vector s in the xz plane, in the plane of the screen. Being classical physics, we could talk about the components of the spin being s cos theta in the z direction and s sin theta in the x direction for this situation. If you remember, in that classical analysis we considered a very small time t, during which the torque made the spin precess to a new position, or because of what we might term rotational mechanics. And this meant that s became s dash, the same size, different direction. We also let d phi be the very small angle that s had turned in the xy plane during that small time dt. It will depend on how you see the perspective here in this diagram, but I've tried to draw it so that the precession is anti-clockwise when looked at from above, and the angle d phi should be clear. In this classical calculation for Larmor precession, we applied the rotational version of Newton's law to the spin s, and we ended up with the final result that the angular velocity of rotation d phi by dt, or omega, is given by GeB over 2me, where B is the strength of the magnetic field, E is the size of the charge of the electron, me is the mass of the electron, and G is the constant from quantum mechanics, which is very closely equal to 2. Now, given that this was a classical calculation which assumed that all the various components of the spin can be measured, it should be clear that we can legitimately write down the three components of spin in the three directions of space x, y, and z. These three components could be called Sx, Sy, and Sz, and it should be fairly obvious that they would be given classically by these three equations. Sx is s sine theta cos omega t, sy is s sine theta sine omega t, and sz is simply s cos theta. Don't forget, in classical mechanics, each of these three components can be measured and known. There's no question here of spins flipping or 50% of this and 50% of that. We can always find the three spatial components of any vector, and that means that in a classical world we can know these x, y and z components of the spin angular momentum s. The component in the z direction should be obvious, I hope. The z component of s does not change with time, even though s is precessing in the xy plane. In other words, the spin s is always at an angle theta to the z-axis as it goes round, so the vertical component sz is always the same. It's constant for a given angle theta at a value of s cos theta. However, the other two components, sx and sy, do change with time. They each have the same maximum possible value, s sine theta, which is the horizontal component of the spin and is the radius of the circle of precession as seen from above, but their actual value changes with time as a cosine function or as a sine function. And being in a kind of circular motion seen from above, Sx has a maximum when omega t or the phi angle is 0, and Sy has a maximum when the omega t is pi by 2 or 90 degrees, and so on. They each keep oscillating as s sine theta rotates. They're out of phase with each other by 90 degrees, and so one can be written as a cosine function and the other as a sine function. If at time t equals 0, Sx is a maximum, then it will be a cosine function, cos omega t. Sy will therefore vary as a sine function, sine omega t. You probably know that when you have a cosine function and a sine function at right angles to one another in space, they combine to give rise to circular motion. And so here we get the anti-clockwise circular motion of the precession when looked at from above. Now once again, this is the classical situation, where we can use the idea of components, cosine and sine, and we can also actually measure and know each of the values of all three components of the spin at the same time. We can actually measure Sx, Sy and Sz simultaneously and know all three. However, if we're starting to learn anything about quantum mechanics, we should be realizing that quantum mechanics isn't like that. Quantum mechanics is all about probabilities and uncertainties, and you certainly can't measure more than one component of the spin at the same time. As soon as you measure one of the three components, you get an answer which is never zero, and which then seems to imply that the other two components must be zero. Then if you measure one of them, you get an answer which is never zero, and so on and so on. So I could pose my question like this: is Larmor precession simply a classical thing? Or does it really happen in some way at the quantum level, and can it be explained by quantum mechanics rather than having to resort to classical mechanics? Can Larmor precession be predicted from the mathematics of quantum mechanics, and can it give an expression for the Larmor frequency? Okay, we know we can't actually calculate the components of the spin like in the classical situation, but could we somehow show Larmor precession from the mathematics of quantum mechanics? Well, the answer is yes, and the approach that is always taken is to work out what we are calling the expectation value of the spin in each of the three directions x, y and z. Note that this is not trying to make a measurement of the spin, it's a calculation of the average of each of the three components of spin as functions of time. Not their average over time, but in a sense their average at every particular time, in order to see how that average changes with time. Each instant of the motion has probabilities for different values, the probabilities of quantum mechanics, and it's that average that we want to monitor over time. Don't, whatever you do, think of it as the average over time. It would also probably be better if we concentrated on the spin magnetic moment mu rather than the spin angular momentum s for this quantum mechanical calculation. If you recall, the magnetic moment related more easily to the energy of the electron in the magnetic field, and as you'll see, we'll need to think about energy in our calculation. So instead of this, we'll focus on this. Mu and s obviously precess in the same way, so our calculation will be valid. We won't have an s in our calculation because our quantum mechanics so far has always thought in terms of spin component, or the direction of spin, as being +1 or -1, but that won't matter. Using quantum mechanics, we will work out the expectation values of the three spin operators, sigma x, sigma y, and sigma z, as they change with time. And we'll look at that calculation in a moment, but what we'll end up with is this result. The expectation of sigma x will be sine theta cos omega t, the expectation of sigma y sine theta sine omega t, and the expectation of sigma z will be the constant cos theta if theta is constant. And omega will be the Larmor frequency, which as before will be given by GeB over 2me. Quantum mechanics will give us the same answer as we got from classical mechanics, and the way to get it is via the expectation value. When we thought earlier on about the idea of the expectation value or average value of an operator, we used these angled brackets either side of the operator in question. So here we have the three symbols for the expectation value, or if you like, the average value of sigma x, sigma y, and sigma z as they change over time. And you can see the sense in which the answers, which we'll find in a moment, agree with the classical calculation. There's no spin multiplier s in these results, of course, no actual value. When we talk about measuring the spin here, we measure it as either +1 or -1 in the mathematics, not spin a half or h bar over 2 or even the letter s. These expectation values can therefore be anything between +1 and -1, depending on the values of theta and omega t, and they can even be 0 at certain times. For example, thinking classically to get your head around these things, when the expectation value in the y direction is its maximum here, plus sine theta, then the expectation value in the x direction must be 0. Let me clarify and emphasize that point. We've been saying all along in quantum mechanics that you cannot measure the components of the spin of a spin-a-half particle to be 0. It is never 0. Whenever you measure it, you must get an answer of +1 or -1, corresponding to h bar over 2 or minus h bar over 2. The measurement of a spin-a-half particle can never be measured to be 0 in any direction. However, you could get an answer that there is a 50% chance of it being +1 and a 50% chance of it being -1. So that if you ask the question, what is the average value, then the answer can be 0. Granted, any individual measurement will settle on one or the other, plus or minus 1, but the average of all measurements can be 0. Any measurement of sigma x can never be 0, but the average value of sigma x can be 0, and this will happen when omega t is pi by 2 or 90 degrees, because cos 90 is 0. So let's look now at how these three expectation values are found from quantum mechanics. Once again, if you feel you don't want to go through this, especially as it brings in some other ideas which aren't strictly needed elsewhere, then feel free to go to the end of this video and move on to the next one. The discussion will, however, re-emphasize the concept of the expectation value, and that might be useful for later. The starting point is going to have to be Schrodinger's equation. Now, we haven't touched on this so far, but students who've done a little bit of quantum mechanics will know that Schrodinger's equation is one of the most important tools in the study of quantum systems. They will also probably know that there are two forms of the equation. The simpler form is known as the time-independent Schrodinger equation, and it looks like this. As its name suggests, it doesn't depend on time. It's about systems which are static, or in physics parlance we sometimes say stationary. I've represented the state vector here, whatever it is, by psi. Don't worry what it is, it's just the state vector of some system or other, not necessarily to do with spin at the moment, just very general. H is known as the Hamiltonian, which is an operator which describes the total energy of the system. I'm sure that even if you haven't done any quantum mechanics before, you've probably realized from what we did earlier that this version of the Schrodinger equation is just an example of our measuring equation in quantum mechanics. You apply the operator h to the state vector psi, and if you get the same state vector multiplied by a real constant, then that constant is a measure of what the operator is supposed to measure. In this case, the operator is the Hamiltonian, the thing that measures energy. And so if we get a real constant times the same state, then that constant is a measure of the energy, so we give it the letter E. However, this form of the Schrodinger equation isn't really going to help us in thinking about precession, where things are definitely changing with time. Things are not static. They are not time independent. The other form of the Schrodinger equation is called the time-dependent Schrodinger equation, and it looks like this. I h bar d by dt of psi of t equals h of psi of t. The state vector now is shown as being a function of time, psi of t, so things are changing. Now, I'm not saying this equation is simple, but the various bits of it should be easy enough to understand. It's saying that if you differentiate the state vector with respect to time, multiply it by IH bar, you can then set it equal to what you would get if you apply the Hamiltonian operator to the state vector. And if you then solve what all that gives you, you will have a description of the state vector as it evolves with time. You can read up on this if you want, and I suppose many of you looking at this video will know it anyway, but one form of the general solution to this time-dependent Schrodinger equation says this: psi of t equals psi not of t times e to the minus iet over h bar. In other words, it's kind of saying, if you know the state vector psi at a given time, the static version of it if you like, and if you also know the energy of that state E, then you can write down the state vector as a function of time by taking the static state vector and multiplying by e to the minus I et over h bar. Easy peasy. Strictly speaking, I suppose, the state vector psi at a given time, the static version, should really be written like this: psi at time 0. In a sense, this is the state vector at the instant you start the clock, t equals 0, and from which time any changes take place, and those changes are then given by psi of t. However, I think I shall leave this part as simply psi, with the understanding that it is the state vector at time t equals 0. So, hold that thought. In a moment we will need to get from a static time equals 0 version of the state of an electron in a magnetic field to a time varying version of that state in order to study precession, and we'll do it by multiplying by e to the minus iet over h bar. Well, here's our static situation as we visualize it. This is going to be our starting point, looking at the static situation, at least a snapshot of it at a particular time 0, when the spin mu or s of the electron is in the xz plane, the plane of the screen, and at an angle theta to the z-axis. So this represents our psi in a sense without time involved. Now, we've already written down the state vector for this supposedly static situation using our z basis. In other words, in terms of the upness and downness in the z direction, this spin is at an angle of theta to the z-axis in real space. It has, in a sense, some upness and some downness. In Hilbert space, we write the state vector of such a spin system as being a mixture of the up and down basis states. We could write it like this. Rather than give it the label psi, I've called it theta z, simply to signify that it's the state vector in Hilbert space representing the spin at an angle theta to the z direction in real space. Remember, what goes into this ket type bracket is only a shorthand descriptor. At the moment, there's no time dependence. These are the two basis state vectors, which in column vector terms are 1, 0 for up and 0, 1 for down. and they are each multiplied here by a constant A or B, signifying how much upness and downness the state contains. Clearly, as the angle theta is less than 90 degrees, there should be more upness than downness. A should be bigger than B. Now, we've already discussed that if the spin were to be measured while the state was like this, then the square of A would represent the probability that the spin would be found to be up, and the square of B would be the probability that would be found to be down. There would be no in between. We also said that the total probability for any measurement should be 1, so that A squared plus B squared, or strictly AA star plus BB star, should be 1. Now, in order to change this static state vector into a state vector with time in it, we need to know the energy E of the state. Then, according to that general solution of Schrodinger's time-dependent equation, it would simply be a case of multiplying this static state vector by e to the minus I et over h bar. Also, because our state theta is in two parts, some up and some down, what we really need to know is the energy of the up state, I'll call it EU, E up, and the energy of the down state, ED or E down. You should recall that when the electron spin is pointing up in a magnetic field, it has a different energy to when it's pointing down. Taking EU and ED as the two energies for now, we can write that the state vector as a function of time should look something like this. Can you see? I've changed the theta state to being a function of time. And to do that, I've multiplied the up state part of it by the exponential containing its energy, EU, and I've multiplied the down state part of it by the exponential containing its energy, ED. This equation, therefore, has four constants in it, A, B, EU, and ED. But in fact, we know them all. Early on, we showed that A and B for this situation, with the spin at an angle theta to the z-axis, were given by cos theta over 2 and sin theta over 2. Remember, we had to halve the angles. Also, when we were discussing the energy of various magnetic moments in a magnetic field, I defined the energy when the spin was at 0 degrees to the z direction to be 0, and calculated that the energy at 180 degrees was 2 mu b. It was also shown that the energy of the down state, 2 mu b, could also be written as h bar omega, where h bar omega was the energy needed to flip the spin from up to down, magnetic moment wise. The angular momentum would go from down to up, of course, for the negative electron, and it was shown that the angular frequency omega was given by GeB over 2me. This happens to be equal to the Larmor frequency, but was shown independently to be this value. Anyway, substituting these four things which we know, A, B, EU, and ED, into our time-dependent state vector for this electron gives this. There are A and B, and there are the two energies. I've put the zero energy in for completeness here, but of course e to the 0 is 1, so this whole thing becomes this. Writing the up and down states in their column vector form gives this, and if we multiply this out and combine the terms into one column vector, this becomes theta of t is simply the column vector of cos theta over 2 on the top and sin theta over 2 times e to the minus I omega t on the bottom. Remember that this is the quantum mechanical state vector for our electron as it precesses. It depends on time. Now, I should say that the fact that the down component is the only one that shows time dependent here is not significant. Don't forget that very early on I could have defined the zero energy as being when the spin was in the horizontal direction, in which case I would have had a plus and a minus h bar omega over 2 for the two energies here. In that case, both these positions would have had an exponential term. It would have made no difference to the answer we'll get, however. It doesn't matter how you define the zero of energy, it won't affect the final answer of the calculation that we're now going to do. This time-dependent state vector for the precession is exactly what we need. But what do we do with it mathematically? If we try to make an actual measurement of it by applying one of the Pauli matrices, sigma x, sigma y, or sigma z, it would not give the same state multiplied by a constant. It would change the state and there would be no measurement. If we want to look at Larmor precession, we need to investigate, therefore, the expectation value of the sigmas for this state, especially sigma x and sigma y, as they're the ones that we suspect will change with time. The expectation value of sigma z should not change, but we could always evaluate that as well, just to make sure. But the Larmor precession is essentially going to be seen in sigma x and sigma y. As has already been explained, in order to find the expectation value or the average value of an operator for a particular state, the mathematics says that you need to sandwich the operator between the bra vector of the state and the ket vector of the same state, and then evaluate it. Let's first do it for the x direction and ask what is the expectation value of sigma x for this time-dependent theta state. To find this, we sandwich the operator sigma x between the bra vector of the time-dependent state and the ket vector of the same state, which is written like this. There's the operator for measuring the spin in the x direction, sigma x, and it's sandwiched between the time-dependent state vector for this situation, the ket vector, and the same thing written in bra form on the left. Now we said that the state vector in ket form is given by this column vector, and the spin operator for the x direction, sigma x, is given by this matrix. But what about the bra vector? Well, you may recall that the bra vector is more or less the same as the ket vector of the state, but you have to use the complex conjugate version of it, and you have to write it as a row vector rather than a column vector. Doing this and putting all three things that we know into this expression for the expectation of the spin in the x direction gives this expression. There's the row vector form of the state vector. It's exactly the same as the one we had for the ket, except that it has been put in row form rather than column form, and also it's being complex conjugated. The minus I in the column vector has become a plus I in the row vector. The comma has been added to the row vector simply to delineate the two parts. It's not strictly necessary. The middle 2 by 2 matrix, of course, is the spin operator for the x direction, the sigma x. So, once this whole expression is evaluated, it will give us what we're asking for, the expectation value of the spin in the x direction, and it will tell us how the average value of sigma x changes with time. We should actually see the Larmor precession in the mathematics. Anyway, the first thing to do in evaluating this is to multiply this column vector by this spin matrix. It should be obvious what this will do because sigma x always simply swaps the up part with the down part. It flips. You can go through the details if you want, but you will end up with these two entries in the column vector being interchanged. They will give this expression. Notice they've been swapped over, and now we don't need the sigma x operator in the middle. It's done its job. If we now multiply these two vectors out in the usual way, it gives a single one-dimensional answer, not a vector. The multiplication involves the first in the row times the first in the column, plus the second in the row times the second in the column, and it gives these two terms to be added up. Notice that these two parts are the same, and so we can pull them out and put the exponentials in a separate bracket. Notice also that we have here the double angle identity from trigonometry, which means that this whole thing is simply sine theta. Also, the sum of these two exponentials is by Euler's formula simply cosine omega t. This means that we end up with the expectation of the spin in the x direction as being sine theta cos omega t. And that's it for x. That's the expectation value, or the average value of the spin component in the x direction, showing how it changes with time. Similarly, if we did the same kind of calculation for the y direction of the spin using sigma y, we would get this expression. And we could also do it for the z component of the spin using the operator sigma z, and we would get this. Let me emphasize what we've just done here. We've not looked at angular momentum S and forces and torques. We've not thought about what we tend to imagine is actually going on to make the electron spin precess, in other words, our classical physics. All we've done is, first to take the state of the electron at a given time, when it's at theta degrees to the z-axis, and written it in terms of the up and down basis states, as is our standard practice now in quantum mechanics. Then, knowing the energies of the up and down states in the magnetic field, we converted this static state into a time-dependent state, following the rules of Schrodinger's equation, which simply meant multiplying by the relevant exponentials. Then we took this time-dependent state and used the standard formula from quantum mechanics to find the expectation value, or the average value, of each of the three operators, sigma x, sigma y, and sigma z. This meant sandwiching each of the three sigma operators one at a time between the bra and ket form of the time-dependent state, and evaluating things in the usual way. And the final results were these. So after what seems like fairly abstract mathematics, we've ended up with three formulae for the average values of the components of the spin, which are more or less the same as the spin components we got from our classical mechanics calculation. As was mentioned before we did the exercise, we've ended up with something that wholly supports classical mechanics with regard to Larmor precession. The z component of the expectation of the spin is constant for a given angle at cos theta, but the x and y components oscillate at an angular frequency omega, 90 degrees out of phase with each other. That's the cosine-sine difference. And they give a precession in the expectation about the z-axis, and the precession frequency doesn't depend on the angle theta. This is very much the same as classical physics, and yet it's entirely different. Classical physics says that for a charged spinning ball, the spin actually precesses, it physically gyrates, and if you measure it, you can monitor its gyration over time. Quantum mechanics, on the other hand, cannot give any more than probabilities. The so-called motion cannot be directly monitored over time in quite the same way. However, in a sense, from those probabilities, an average value of the spin has been calculated, an expectation value which changes with time, and this predicts a kind of gyratory motion. And the precession frequency is given exactly by the classical mechanical calculation, assuming the quantum mechanical factor of g is also included. Now, this digression into the quantum mechanical description of the Larmor frequency, as I said before, is not strictly necessary for understanding entanglement, and will maybe seem especially unfair as it touched upon the Schrodinger equation, which I didn't intend to go into. However, when Larmor precession crops up, although like most people you will probably think of it in classical terms, you should now be convinced that quantum mechanics doesn't deal with it as though physical objects were actually precessing. It emphasizes the point that it's all about probability, and it's that fact that will be important when we come to think about entanglement. Okay, we have done all that we should need for the single electron as far as the quantum mechanics of its spin is concerned. In the next video, we'll move on to thinking about the quantum mechanics of two electrons together. They may or may not be entangled at this stage, but we need to have the mathematics sorted in order to discuss them. Then, in a later video, we can look at what goes on when the two electrons are entangled.